So let's welcome Professor Dr. Ekkehard Peik from PTB, Germany. And topic of the talk is nuclear clocks for testing fundamental physics. Without wasting any time, I will now hand over the stage to Professor Peik.
Thank you very much. Good morning. It's a great pleasure for me to speak here today, and I'd like to thank the organizers for inviting me. We had a nice variety of interesting different subjects this morning already, and I think my talk is going to add just an additional topic to it. I think many of you are familiar or quite experts already in atomic clocks, and I'm going to speak about an aspect of a novel aspect in the field of atomic clocks, which we call nuclear clocks, and I will explain what I mean with this and what is the status of this. Maybe a few more words about of introduction about my institution. A few people ask me, so PTB is a German National Metrology Institute, a government institute. So the British equivalent would be NPL. The US equivalent would be NIST. So it is concerned with everything related to measurement and of course time and frequency measurement is one very important aspects. Braunschweig is a small town somewhere, I would say, between Berlin and Hanover, and PTB happens to have its main seat there. Seems frozen.
Yes.
Yeah. Okay. Okay. I'd like to start with a little bit of an introduction on the connections between atomic and fundamental physics. And you can see I try to schematically show here how close these connections are. Of course, the foundations of quantum theory, the development of quantum theory was, of course, very closely related to the question of understanding atomic and nuclear structure. So to describe matter, quantum matter, people understood that a new theory would be required, that it cannot be done in classical physics. And the data that was driving this field mainly was spectroscopy data. So it was atomic spectra. I'm showing examples here, like the Fraunhofer lines in the solar spectrum, or then there's the sodium line seen in the solar spectrum, and you see it on Earth in the laboratory as the emission spectrum. And this is, of course, the data that was driving the development of the theory. And then people in spectroscopy recognize that some of these lines can be reproduced with very high signal-to-noise ratio and very well reproducible frequencies. And so it turned out that actually they could be used to measure and to define frequencies. So that was the idea, to go from spectroscopy to clocks. And I'm showing some examples of clocks here. This is the hydrogen maser that flew on the Gravity Probe A mission to check the gravitational redshift during the Apollo time. This is a modern optical clock that we have in our laboratory. And now today, the accuracy of these devices has developed so much that they can be used to make meaningful test experiments of fundamental physics. And now the circle kind of closes, as today we are also applying these clocks to perform tests of the foundations of these underlying theories, like testing Lorentz invariants, looking for possible temporal variations of constants, or using clocks in high precision astronomy, like for taking this picture of the black hole. So a very close interaction of these fields between the measurement devices and the foundations of the theory. This is a picture of like an aerial view of our clock laboratory in Braunschweig. It is, for historic reasons, it's a large laboratory space It is so large because people in the 1960s, when this was planned, thought that cesium clocks would develop in the sense of becoming bigger. Atomic beam devices, one would have a long interaction time. So how to obtain a long interaction time? Well, that is having a large apparatus. And so people prepared here like a 20-meter hall for a huge beam machine. It was never built. But today, this is our main laboratory. We use it for a variety of purposes. So you can see here, just to show you, I think it's a unique place because of this ensemble of clocks that we have here. There is 2 cesium fountains. These are the primary cesium clocks that we have in Germany to define the SI second and to generate time scale. And then all this here is an all ensemble of optical clocks. You can see ytterbium plus is the ion of choice here. We are doing some combination of ytterbium and strontium. Here is the one that we developed already together with industry as a transportable version. On the campus of PTB, actually, there is more work on optical clocks in other departments. There is also work on a lattice clock with strontium. There is work on highly charged ions, and it's a larger ensemble. So today I'm actually going to speak only a few selected aspects, and my main feature will be the work towards the development of the nuclear clock. But I couldn't resist to show you a little bit a recent highlight of this ensemble of optical clocks with the ytterbium plus ions, because we made some nice progress in these violations of local position invariance. The subject that was touched yesterday already, the question is there possibly any time derivatives in the fundamental constants? And we are tackling this question with the ytterbium ion. Well, this is a simplified level scheme of ytterbium plus. It is a single ion trapped in a radio frequency Paul trap, laser cooled, and then we can do very high resolution spectroscopy. And what's nice about the ytterbium plus, it has 2 different forbidden transitions. So there is the ground state has a single 6s electron, and then either one can excite the 6s electron to the 5d orbital, which change of 2 units of orbital angular momentum is an electric quadrupole transition. So it has about a Hertz line width. And then there is an even more strongly forbidden transition opening the closed 4f shell here, promoting one of these f electrons to the 6s shell. This is a change of angular momentum of 3 units, so it's an electric octopole. Strongly forbidden. The lifetime of this excited state is more than 1 year. And this state has very nice spectroscopic properties, because the spectroscopic relevant electron is basically now a hole in the inner 4f shell, and it is surrounded by the spherically filled 6s shell. And this reduces a lot of external influences on this state, and so the state has very small systematic shifts from external electric fields, for example, and we can control the frequency very well. And what's extremely nice about the system is that we have these 2 different frequencies. You can see the electronic structure is quite different, so they also have different sensitivities to the value of the fine structure constant. A hand-waving explanation: the 4f electron is much closer to the nucleus than the 5d electron, so it is much more relativistic, and therefore the relativistic contributions to this stage are much bigger than in this case. And it means that the ratio of the optical ratio of these 2 transitions is sensitive to the value of the fine structure constant via the relativistic contributions, with the sensitivity enhanced by a factor 7. This gives us a very nice experimental opportunity, because we can directly measure an optical frequency ratio. We do not have to use microwave cesium clocks, although we have them nearby, but we don't need it for this experiment. And then we have this enhancement sensor. So if we have like a 10 to the minus 18 uncertainty for the frequency ratio, we can divide this by this factor 7 and get into the 10 to the minus 9 range of sensitivity for changes in alpha. And we did measurements now already. We are running one of these clocks nearly continuously over the past 2 years. And so this is a record now spanning like 6 years. All these are individual frequency ratio measurements here. On this is what is it? This is the 10 to the minus 16. Yeah, 10 to minus 16 scale, then we can look at all these data and see is there violations of the present model. So is there a drift of the fine structure constant? So this would be from the fit of the dashed red line here, which is just a linear fit in time, and the blue curve here is a fit to a potential yearly variation as Earth rotates around the Sun on this elliptic orbit. The gravitational potential of the Sun on Earth is changing in a known and predictable way, and we fitted the clock reference data here to both effects. And I only like to point out this one result here. So for the linear drift, we have now this value here. The relative drift of the alpha dt would be in the range of 210 minus 19 per year, and the uncertainty is a bit larger than the value, so it's consistent with 0. And I'd like to emphasize also 10 to the minus 19 per year. You know, the age of the universe is about 10 to the 10 years, so even extrapolated with the age of the universe, it would be a very small change that would still be consistent with this spectroscopic data. Of course, speaking a little bit about cosmology, we would not be allowed to extrapolate back to the Big Bang. Of course, in the beginning, there was, of course, much more important possibly dramatic changes, but we are doing an experiment now in the year 2020 and in an Earthbound laboratory. And for this laboratory, we can give the statement now, which is very low uncertainty. Yeah, this was just to give you a little bit of flavor of this, of what can be done with the optical trapped ion clocks. You can see also here a nice plot on this, the uncertainty, the evolution of the uncertainty in this quantity field that has been tackled for now more than 20 years, using different combinations of atoms, and you can see very nicely with the new results here. It follows, like, I can call this a Moore's law of the alpha dot change. So it has been nearly logarithmic progress over time, of course, reflecting the lower and lower uncertainty of the optical clocks, together with the use of more sensitive of systems with higher sensitivity, like the ytterbium. Plus, Dmitry Mutka yesterday spoke about the Symposium system that was used earlier on already. It has a very high sensitivity also, but somewhat lower uncertainty. Okay, with this, I'd like to switch to the nuclear clock, and the nuclear clock is in some sense nothing but an extrapolation of the concept of the atomic clock. So the fundamental scheme remains the same of the optical clock. So just to remind you briefly I've drawn it here. So we have a quantum atomic two-level system where the energy difference defines the frequency. We are driving the system resonantly with a frequency stable laser, and then there is some servo loop from state detection of this atom. We derive a steering signal that we apply to the laser in order to keep the laser frequency in resonance with the atomic reference frequency. And then we need an optical clockwork, which usually is a femtosecond femtosecond frequency comb, and from this we can produce a countable frequency or a time scale. The generic scheme of the microwave atomic clock, of the optical clock with atoms. And now for the nuclear clock, I'd like to explain here what we are doing. Basically, is we are replacing the reference system. So instead of the atom with the resonance in the electron shell, we are looking at the resonance inside the nucleus, an electromagnetic gamma ray, one may call it, resonance inside the charge distribution of the nucleus. And this is, of course, now has some important differences. We heard it already this morning from Peik that was pointing to the nucleus as one example of the composite system, and then he said it's not friendly, it's too small, and of course that's true. I agree completely. but there is for the clock, there is some nice features, because here the charges that we are driving, they are very densely bound. It means it's much harder to influence them from the outside. So an outside perturbation, like an electric field, a patch field, a collision with another atom or so, has relatively much less influence on this charge distribution inside the nucleus than it may have on the charge of the electron. And this is why we think that the nuclear clock promises both a higher accuracy and a higher stability. Higher accuracy means because we have less sensitivity to external perturbations. High stability because we can potentially work not with a single or a few atoms, like in laser cooled with trapped ions or in lattices, but we can potentially go to a solid state and then work with 10 to the 16 or so nuclei, and hopefully getting a stronger signal and a higher stability. And of course, also I would like to briefly explain, we expect high sensitivity to new physics, like to the aspects of changing fundamental constants that I've mentioned already. Now, there's of course a severe challenge that the strong binding of the charges means, of course, it's the energy scale is a completely different one than we know from the valence electron in the atomic shell. So here it is the electron volt scale and the optical scale, and the lasers are of course also running based on electronic transitions. So here typically the typical energy scale would be the mega electron volt, or so something that's not accessible with the laser technology we have today. But there's a nice present from nature. There is one exception to this statement. There is one specific nucleus, an isotope 229 of thorium, and it has an unstable nucleus, it's about 8,000 years half-life, and it is unique in having a very low energy nuclear transition in the range of about 8 electron volts. This vacuum ultraviolet radiation. And this is a system that we have selected, or it is the only system available to test, to investigate this concept of an optical nuclear clock, because we believe it is accessible with the precision laser technology that is available. So a very special system from nuclear physics that we hope to drive with a laser. On the chart of nuclides, so this is here all the data on known isotopes, plotted as a function of the proton number in this direction, neutron number in this direction. So there's this valley of stable nuclei, and this thorium is located here. What is plotted here in this color code is the energy of the first excited state. So showing the energy scale of this nuclear physics, and you can see some obvious structure in this diagram. So red means high energy, strongly bound nucleus, and they appear here in lines, and these are the so-called magic numbers, shell closures, like the rare gases and the periodic system of the elements. So this is a shell closures inside the nucleus. Shell closure means the nucleus is very tightly bound, and tightly bound means also the first excited state, it has a high energy. So in order to find lower excitation energies, we need to stay away from these lines. And you can see the lower energies in color code green here, they are becoming more frequent here for the highest masses. So that's where the systems become more and more coupled, have more and more degrees of freedom. They may be rotating collectively, but the collective rotation is still at an energy of like several tens of keV. So this 8 eV transition energy here in thorium is really an internal excitation, and what the microscopic origin of this low energy is not really known. But this is just to make plausible, it's in a range where there is a very dense and complex nuclear structure. On the same data in a different presentation. So this now really gives the energy on a logarithmic scale, and you can see how much of an exception the thorium 229 is. So here you see it's a logarithmic scale, it's maybe hard to reach. It's a factor 10 in energy each time. So this is 100 keV, most of the excited states, 100 keV to MeV, and then orders of magnitude below. this thorium-229. And you can also see it's the only one that's known. There's one in the uranium, which is about 80 eV, and then there's one in scandium here, 13 keV. So really a unique system, but we think a very interesting, very useful system. So this summarizes everything that is known about this nuclear system so far. It is investigated, for more than 30 years. Now already it's written here like a two-level scheme. The energy, excitation energy, about 8 eV. It is a magnetic dipole transition. In terms of forbidden transition, it's not very strongly forbidden. It's still a dipole, a magnetic dipole. If it would be in the electron shell, the lifetime would maybe only be milliseconds or so, but since it is in the nucleus, the magnetic moments of the nucleus, of course, being much smaller, but even the magnetic dipole in the nucleus then has expected a lifetime of maybe 1,000 seconds. And then the other aspects you can see in these numbers, the magnetic moments are given here. They are, of course, about 0.4 standard, what is expected, but now in nuclear, not in Bohr magnetons, but in nuclear magnetons, so 2,000 times smaller than the electronic magnetic moment. Another number that's important here, the capital Q, is the electric quadrupole moment. So this is like the asymmetry of the charge distribution, and that is something that worries us in the ytterbium ion clock, because an asymmetry of the charge distribution would couple to an electric field gradient that it would give rise to a so-called quadrupole shift. And now you can see the quadrupole moment. It is not zero, but it is known. We have measured it for the excited state, also for the ground state. It was known. It is 10 to the minus 28 e meter squared, and this is about 8 or so orders of magnitude smaller than a typical electronic quadrupole moment. And this is just reflecting the fact that the nucleus is small. So the nuclear size is like typically 10 to the minus 14 meters. So you take the square of it, multiply it by E, and then you get this typical quadrupole moment. And this shows, this is now a bit hand-waving, why this transition should be a precise.
What is the difference between the red and the black numbers here?
The black numbers. Oh, sorry. The black numbers is all for what was. This is for the ground state. This is expectations, and these are recent measurements. That's why recent measurements on the altimeter. That's why I put it. So I should. This is data taken over the past 2-3 years or so. The energy is most precisely now measured from an experiment at CERN, published last year. I'm going to say a little bit more about it. And this is from hyperfine studies that we did on recoil ions in 2018. Was the first measurement of nuclear moments of the excited nuclear state. Hyperfine measurements based on electronic transitions, so to infer the nuclear. But so to conclude on this idea of the high precision of the nuclear clock, the nice feature is that we are mainly interested in the nuclear transition, but we still have, of course, an electronic environment. So we work either with a 1+, 2+, 3+ ion or inside a solid. So we can somewhat tailor and select a suitable electronic environment. And this gives us a way to select the composite quantum numbers, the angular momentum and so on, of the system in order to reduce these systematic fields shifts like coupling to the external fields. This was here our paper I wrote together with Christian Tamm in 2003, which was where we pointed out these opportunities and which kind of started the motivation this field. So it's really one can avoid. We showed in this paper that one can avoid the coupling to electric and magnetic fields to a degree that is not possible in any electronic atomic transition. And this is somewhat the nice feature of the nuclear. The other thing I'd like to also to briefly hand-waving explain why is it so interesting for fundamental tests. It was first pointed out by Victor Flambaum that this system would, for example, the question I mentioned about changes of the fine structure concept, it would bring an extremely high sensitivity. I spoke about this factor 7 enhancement in the case of the ytterbium plus. here the enhancement, we don't know it precisely today, but it could be expected to be maybe 10 to the 5 orders of magnitude higher. And I can give you, there's more details in these references, but I try to give you a hand-waving explanation. So there's these two nuclear energies of the ground state and of the isomer. And the nuclear energy scale is the mega electron volt, but by chance, these two states happen to be nearly degenerate to this very small interval of 8 eV. But if we analyze the nuclear energy, it is composed of several contributions, or notably there is relatively easy to analyze. There is a Coulomb contribution from the proton charges, and then there is of course a strong binding it together. And this is the strong force contribution is depicted as red here. Now, in exciting the nucleus, we know that the charge distribution changes, and so the Coulomb energy certainly changes by something like 100 keV or so, or maybe even more. But the next result is nearly no energy change. It means that this change of Coulomb energy must be compensated by nearly equal opposite change in the strong contribution. And this is like a magic situation, because it depends, of course, on the present value of the coupling constant for the electromagnetic interaction, for the strong interaction. And if these would be allowed to change, then the influence on this energy would, of course, be very highly enhanced. This is a sensitivity factor 25, and this is an aspect that adds to the motivation to study this. Okay, so far this is for the motivation on to study the system. Now I'm going to speak a little bit about the experiments that are going on in our lab. We don't have it running the clock because we are still maybe far away from it, but we are making good progress with the experiments. One important challenge is for exciting this was the isomer energy. Now it's very small energy. We can only infer it from gamma energies within there is a nuclear level scheme. It is known for this, and one can try to infer the small energy difference. But now, as a difference of large 20 keV, 50 keV, so this was a very tough problem of gamma spectroscopy. The first very important measurement here was published in 1994, and people said it was 3.5 electron volts. That was, many people were excited that would be still in the visible range. And then in 2000, we had started based on this information. Then 2009 came the improved result showing that no, it's not 3.5, it's 7.5, shifting it to the vacuum ultraviolet. But now over recent years, especially like past 5 years or so, there's been a number of now consistent and much more precise measurements. So the final uncertainty of this experiment, a very special experiment done at CERN, published last year. It has to be done at CERN because the nucleus, the isomer, is produced from a short-lived actinium isotope, an experiment that could only be done online at the Soldi facility. But now there is a 10 terahertz uncertainty that remains as a search range for the laser transmission. So based on this information, we decided to build a laser system for this challenging 150 nanometer wavelengths. And the way to do it is 4-wave. We selected the way to do it by 4-wave mixing in xenon. Xenon happens to have a 2-photon resonance at about 12 eV. So we are shining 3 photons into this xenon atom, 2 that are close to these 2-photon resonance, and then they are mixed with a tunable infrared photon, and then the difference frequency is emitted as tunable VUV. And this is one of the efficient ways of producing a tunable vacuum ultraviolet radiation, and it produces this tunable in a relatively wide range around these 150 nanometers, and providing a good spectral density. Of course, it's a highly nonlinear process, so it requires high intensity pulse lasers. So the system we have set up consists of 2 seed CW lasers in order to produce the frequencies of these two photons. We want to know this frequency because it determines the difference frequency here. But then in order to get this nonlinear process in the xenon running, we need to have use pulsed amplifiers. This is 1 joule pump pulse energy and going into a dye amplifier and producing nanosecond pulses of like millijoule or so. And then this is superimposed in a xenon gas cell. One has to get the right pressure and the right alignment of the beams in order to have the phase matching. And if everything is right adjusted, then we get a pulsed UV radiation out. This is relatively straightforward. People have built such systems in the 1990s or so already. Challenge is now, of course, now this is now vacuum ultraviolet radiation. That is, we can no longer work on a standard optical table. This radiation would be absorbed by the oxygen in air within less than a millimeter. So oxygen is completely black for this radiation. So from then on, everything has to be under vacuum. And I guess, yeah, many of you are working on optical tables with aligning mirrors and lenses. And now imagine you need to do this under vacuum. It is a challenge. Of course, we try to minimize. It's basically 2 adjustable mirrors here, but then we need to focus and to adjust this to the eye trap. But it can be done. A few pictures from the laboratory. Yeah, you can see part of these early stage lasers are still commercial devices, and then here starting the vacuum beam line. The DUV can be seen. We can see it on a phosphor. The pulse duration here is like a few nanoseconds. And then here you can see this beam line going through the vacuum chamber of the ion trap. One needs to be very careful. You can see it's all metal sealed, ultra high vacuum. This is because these 8 EV photons are doing photochemistry. So if there would be some residual gases, they would break them and producing contaminations on the optic. One has to be very clean in order to avoid this. And we coupled the system to the ion trap with thorium plus. And in order to characterize the source, we performed some spectroscopy of electronic transitions of the thorium plus, not yet the nuclear, it's electronic spectroscopy. The data on this, there's many. Thorium plus happens to have a very dense level structure, but which is of course not tabulated. Nobody looked at this so far, but the level structure is very dense. So tuning this laser a little bit within a few hours or so, one finds a resonance, and we can do very nicely then see fluorescence from the excited state. The second photon from this already leads to ionization. So producing from thorium plus, producing thorium 2 plus. They also remain trapped in the trap, and we have another laser system detecting electronic transition of the 2 plus. And so while scanning this resonance, so we are building up, we're decreasing the 1 plus population and building up 2 plus population, and we can detect this. This experiment was mainly done to test the laser system, to check the line widths, and you can see it's in the range. This is the line width of this electronic resonance is plotted as a function of the VUV energy, which is like up to 10 microjoule. Then we see some saturation broadening, and if you go away from this broadening, you have like a 5 gigahertz line width of this size. And it is not very high resolution as we have in the atomic clocks at present, but it is for this spectral range, I think, one of the highest spectral power densities, and it's available in the laser system. And so it is what we use for searching for the nuclear fusion. And that's what we are doing at present. So we decided the excitation rate of the per ion is still relatively low. It's maybe 10 to the minus 8 per pulse. And so we thought it's not very promising to try this with 1,000 ions or so. But instead, we decided to join forces with a group of Thorsten Schumm in Jena. And his group is the pioneers in producing thorium-229 doped calcium fluoride optical crystals doped with the thorium. The challenge here is that, yeah, it's a radioactive isotope, so one has to be very careful. There's only very microgram material available, and one has to develop the techniques to grow these small crystals. This was done at the Atomic Institute in Jena. And inside the calcium fluoride crystal, the thorium is present as a 4 plus ion. That's quite nice. It means the electron shell is in the rare gas-like ground state, and it replaces one of the 2+ calcium ions that form this this crystal, and then of course the charge, in order to get the charge matching, replacing a 2+ by a 4+ means one has to get 2 additional fluor minus for the charge combination. But then this is a lightly doped crystal, and the bandgap calcium fluoride was selected because of its good transparency for the UV radiation. It has a high band. But in running this experiment, and we are doing it for some time, we encountered a number of problems. I think we now understand them pretty well. But in the beginning, it was tough. So we noticed that we saw radiation damage from the combination of the ionizing radiation together with the VUV light. Fluorine gets lost. We were very surprised. It's a very strong chemical bound calcium fluoride. Nevertheless, the combined action of the VUV drives the fluorine out, and then the optical transparency is lost. This can be avoided by cooling the crystal with liquid nitrogen, but then working at liquid nitrogen means that residual gases may condense on the surface. And if you look at the tables of water ice or CO2, you find it solid. They have a band gap of maybe 7 eV. So a few nanometer of ice, of water ice on the surface, make it black for the, so that's the unpleasant experimental problems. But now we have found a sweet spot where we can avoid those problems, and we are quite confident about proceeding with this experiment. Yeah, so that's the status on the search. How much am I doing in time? Okay, I'd like to maybe spend 5 minutes on a slightly different experiment. I'm going to show you a little bit of experimental development. This is an apparatus to trap and cool the 3+ ions. So the 3+ charge state I mentioned already. 4+ is a rare gas-like electron shell. 3+ is 1 valence, and one would expect it, hand waving me, because of 3+, to be also in the EPUV or VUV, but it turns out there is some fine structure transition, so that makes the 3+ actually available to laser spectroscopy and even direct laser cooling at about 1 micron, 600 nanometers, a few optical transitions. So that's why this is a favored charge state for the trapped ion optical clock. But it's relatively hard to get this if we just work with a microgram or so, or nanogram source, and trapping, producing a 3+ ion is hard for trapping. And we decided to not to set up an oven in the ionization. So we are producing these as so-called recall ions from uranium. So we have uranium 233. It's a mother isotope. Decay of this produces the thorium. The alpha decay gives a recoil energy of about 80 keV to each freshly produced thorium. So it is ejected from the solid. If it's close to the surface, it's ejected from the solid. But then one has a beam of 3 ions in this in higher charge states. But of course, one needs now to get rid of 80 keV here in order to arrive at nano eV or so laser cooling. And this has to be done. This is done in collisions with helium buffer gas. But then we have several differential pumping stages or so in order to get from like 100 Pascal helium here to get to an ultra high vacuum here. And this is why this is a relatively complex apparatus with ion optics and things. And the other thing that we are trying here is I mentioned the level scheme of the 3+. In principle, it could be directly laser cooled, but it's the lines are relatively narrow. And so we decided to use sympathetic cooling with strontium. I can show you some results on this. So this is a combination of thorium 3+ Coulomb crystals of thorium 3+ ions depicted in red and strontium 1+ ions depicted in blue. We selected this combination because the charge to mass ratio is relatively similar, 80 to 1, 80 mass, strontium mass 88, 1 charge, mass 20, mass 20, 229, 3 charges. So they remain within a power trap, they remain closely coupled, which is important for this efficient sympathetic cooling. So different types of Coulomb crystals. So here this is like a linear string of these thorium ions inside a large cloud, a large crystal of the strontium plus, or this is 2 times 500, so there's a cigar-shaped crystal inside. And this will allow us to have a nice ensemble of laser-cooled thorium inside on the axis of this trap. And we recently succeeded with the experiment. So these are pictures of laser-cooled strontium crystals. So we are only shining in the strontium laser. So everything that you see fluorescence here is the strontium plus ion. And the thorium lasers we did not yet turn on here. So they appear as dark spaces. So in a linear chain, so this is only strontium. Then we inject 2 thorium 3+. You can see the higher charge produces a stronger repulsion. So this dark state here is a bit wider than the average distance between the strontium. It's a simple exercise to calculate the structure, and so this shows the result of the calculation. And the red dots is where the thorium should be sitting. And this is our larger structure. So it's a bit like this picture here. So a few hundred strontium, and then we are injecting here like 12 thorium plus, and you can see the dark ones in the center of these. And here we have injected a few more, and then you can see this dark region gets bigger. And now this is a nice sample of sympathetically cooled thorium 3+ ions. The recoil source also has a nice feature. It produces not only the nuclear ground state, but also the isomer. So it will allow us also to do hyperfine studies of the isomer without having to excite it with a laser, as long as we are searching for it. And so we, as a test of proof of principle, we did some spectroscopy of these of optical transitions here. You can see that we have like few megahertz Doppler widths, means laser cooled thorium resonances here via the sympathetic cooling. Okay, with this I'd like to conclude. So this is like the roadmap and frequency uncertainty. We need to go towards the nuclear clock. We are now still in the range here of the gamma spectroscopy. We hope to be very soon here in the range of the gigahertz with the laser source that we have. We could do interesting studies of different electronic environments already. And then in the next stage with a different laser system, one would then go to the kilohertz or hertz range of resolution, where one could really start to do competitive fundamental tests and clock operation. So I'd like to thank the team and our funding sources. At presently, we are funded by an ERC synergy grant. If you are interested to join, we have open positions also. Please come talk to me, and this is I'd like to conclude, and thank you for your attention.
It was very interesting and informative. And now it's time for questions. We have time for few questions.
If you were to put your VUV laser into your Coulomb crystal and attempt to observe the transition, how would you go about detecting that transition?
Oh, right. That's an important question I didn't mention. So for the crystal, we have these for the calcium fluoride, we have the very large numbers. So we just try to detect fluorescence. With a smaller I number, the idea is to detect this in a double resonance scheme. So driving the nuclear transition would change the nuclear spin, would change the hyperfine structure, and we can read this out on the electronic transition. So this is a double resonance scheme, and it is very efficient because it is, of course, it is very similar to what is done in the atomic single ion traps to not to detect the fluorescence on the forbidden transition, but to measure it in a double resonance scheme. And like this, we can, it's even a quantum non-demolition detection, and it allows to detect really with unity efficiency every nuclear excitation.
The transmission you need to probably on the smaller time scale was linear layer or maybe non-linear layer. Calculated, but
It would not, I must say.
should not, yes,
Yeah.
should not, yes. But what about maybe spectroscopy data from astronomy from distant objects? What they tell us about?
Oh yeah, that's well. I'm not the expert. I should say, yeah. There have been these astronomical observations where people looked at quasar absorption spectroscopy, looking back like 10 billion years or so. I would say in the again, I'm not the expert, the expert, but speaking to cosmology, I think everything happens again on a logarithmic scale. So within the first 10 to the minus 30 second, that was where the dramatic changes happened. And so, and very hand waving, I would say maybe 10 billion years ago, it looked the same like it is today, but or more solid foundation, please talk to an astrophysicist. The other difference is that people point this out sometimes. Well, this is an earthbound experiment, of course, whereas the people looking at quasar spectra are looking at interstellar matter. So not gravitationally bound and very different gravitational field. One should also be careful. There could be, if we're speaking about new physics, one should also maybe allow that it's not exactly the same conditions.
Might be disconnected from the but with different gravitational.
Could be, yeah. But in fact, I think it's really the laboratory experiments we can do very precisely and reproducibly. Everything else, astrophysics is of course a different game of doing observations in inaccessible parameter space that's inaccessible to the laboratory. But of course, it can much harder to do tests of reproducibility.
If you have any more questions, you can approach Professor Peik during lunch.
What are the expected systematic changes
You mean for the clock? For the trapped ion clock, basically, so the field-induced shifts, I would say, can be brought to a negligible level. So what would remain would be just the standard relativistic things, time dilation, second order Doppler effect. That would, of course, be for the nuclear, for the electronic transition, it would be the same. So it would be important to get the good cooling, to get quantum control of the state. That's for the ion trap. In the crystal, there would be coupling to the crystal fields, to phonons. So it means the crystal also would need to be cooled to maybe liquid helium in order to freeze out the phonons, again, to get rid of relativistic Doppler effect.
So let's thank again Professor Peik.